and 3 on the official program. So the way I'm going to do that is confine the official lecture to before the break, roughly, may go over slightly past that. And then the section after is left for more of an informal open discussion. I think there will be a lot of technical details we'll want to fill in here, but we can do it less as a formal presentation and more as a discussion. This is a review of what so far is a topic consisting of approximately 1 paper, actually approximately 2 papers. I have been enthusiastically, this gave me a wonderful deadline. Deadlines are useful for trying to get a paper almost ready for submission. Basically, so my approach to writing papers is usually everything that I would ever want to know, I would put in the paper rather than, anything that I would wish someone would tell me, I try to put in the paper. So this really is more of a pedagogical introduction, both to many aspects of rotation. So a lot of things that on Monday you were asking for, it's somewhat written up in here, plus there are references to other textbooks and resources for further information. So basically the whole analysis technique is spelled out. Now there are 2, so we will, let me therefore start these going around. You'll need these in the exercises later as well. So you have a massive preprint. You're not responsible for reading it all over lunch. On the flip side, if you catch egregious errors, I found at least 1 typo still in there that was introduced by weird editing a couple of nights ago. Any major flaws, do let me know before I submit it. So there are 2 topics here, though, basically. We're combining collective behavior, and rotation in particular, with ab initio methods. So this talk will basically be an introduction to 2 distinct things, rotation, which you've seen a little bit of already, and ab initio methods, and then we'll see how they fit together. Which is actually very interesting to me, to actually see the 2 coming together. First, though, I couldn't resist. A few weeks ago in Berkeley, I happened across this and realized that this should be the poster for this conference, or for this summer school. Right? You're learning physics with fun models. We have both Model Calc and ARB Model, our versatile construction system. And I haven't counted, but I suspect we probably have at least 14 models, probably more than 14 models in this summer school. You can't read the small print, but the small print is always very important. This set may contain contains parts that may be harmful if misused. And, oops, something just happened. Oh, okay. Read the manual carefully, of course. And it's not to be used by children except under supervision. And you've noticed that we do have the faculty around during the afternoon sessions. Okay, so ab initio nuclear structure is a major effort within nuclear theory. And it's basically approaching what I think is the fundamental problem of nuclear physics, which is getting a first principles understanding of nature, understanding how nuclei can come from the next level down of physics, QCD. You want to then be able to predict basically everything about nuclei, levels, rates, cross-sections, in general, the things even where they cannot be measured, that's where it's most important to be able to predict them. Now, ab initio methods will, as far as anyone can tell, only be able to get so far. If this is a nuclear chart, you might be able to solve 20, even 40 nucleons coming from just the nucleon-nucleon interactions. You'll probably still need effective theories, be it shell model, density functional theory, whatever, for heavier nuclei, but ab initio approaches can serve as a bridge to that. If you are in the US, you probably have seen extracts from the long-range plan. These are the challenges that the US community at least set forward. And so ab initio theory fits into this in terms of finding out what are the origins of simple patterns in complex nuclei. That's very much the emphasis of today's talk. And then what is the nature of the nuclear, this can feed back into asking what is the nature of the nuclear force that binds these protons and neutrons, working backwards from the many-body system. So there's a flow chart of sorts. We have quarks. There would be the step of going from quarks to the nucleon-nucleon interactions, either by solving on the lattice or through effective field theory methods. Then, once you have the nucleon-nucleon interactions, you need to be able to solve the quantum many-body problem, define the nucleus in terms of those nucleons, and that's the emphasis of today's talk. Beyond that, then there's the ambitious step of once you understand an individual nucleus, calculating, ab initio, calculating from that reaction dynamics, which there are people working on, for instance, the Livermore group. So we have this picture of the nucleus as being a bunch of interacting nucleons, but then we have these patterns that emerge. The first that we see is shell structure, and then there are these collective structures coming out. Deformation, pairing, which you'll be learning about a bit next week, cluster correlations. In principle, at least, that all comes out from solving the many-particle Schrodinger equation for those nucleons. So it's a Schrodinger equation in 3A dimensions, plus a few spins thrown in. So solving the Schrodinger equation, that should be easy, trivial. This is all a trivial problem, right? I think most of you know by now that that's our biggest challenge we're facing. So isn't it wonderful when you can reuse slides? On Monday, we saw this in a slightly different context. But the question is, how can we solve this many-dimensional Schrodinger equation? And the basic approach, again, is solution in a basis. Our basis will be a little bit different this time from Monday, but actually there's a lot of overlap. So just as a review, what are we doing? We're taking a differential operator, the Hamiltonian, and rewriting it as a matrix operator. And we do that by taking our functions and re-expressing them as a set of coefficients on a bunch of basis functions. The idea, again, being here in one dimension, if we needed to produce the black wave function, we'd get it out of these red basis functions, add them up in the right proportion, and you'd get the final function. And this matrix eigenproblem lets you solve for those coefficients. That's one particle in one dimension. Now, we really are working in 3 dimensions, not 5 dimensions today. And we will be using the oscillator basis. There are other bases, and in fact, that's one of the things I'm interested in playing with. But the traditional approach for various technical reasons is to work with an oscillator basis. That actually makes sense. We all know that as a starting point, the nucleons that seem to be moving in sort of a mean field that looks sort of like a harmonic oscillator, because everything looks sort of like a harmonic oscillator. And the idea is, okay, we get out, in the end, what matters is our basis functions are a radial function times a spherical harmonic, and our radial function has whatever this form happens to be, some Laguerre polynomial. And the other important thing, again, is that any oscillator has an h-bar omega parameter. That's basically the spring constant. Yes?
Just a question on the potential use in the addition method.
Yeah.
That can choose to be, you're constructing the different
Yeah.
interaction. Does it mean two-body interaction, three-body interaction, or more?
So, okay, and so that's actually an important difference, and we'll get to a little bit more, between the shell model and the ab initio approaches. The shell models tend to say, here we have some mean field potential that our particles move in, and then we add in some little correction in the form of a two-body force. For these ab initio approaches, we're not setting up any mean field. One may it may turn out that our wave function in the end looks like a mean field wave function, but we are setting up a Hamiltonian, which we can discuss more informally in the second half also. The Hamiltonian is the kinetic energy plus these pairwise and, in general, 3-body. And in general, there would be higher body. Very few people are set up to handle that, but there does seem to be a hierarchy, as people hope, and there's some evidence, at least to this effect. 2-body, most important. 3-body is a bit of a correction. 4-body, you may be able to get away with leaving out. So actually, the calculations we'll look at today are done with a 2-body interaction. It's much more costly to work with a 3-body interaction. So if you can get away with the 2-body interaction, that's great, but ultimately you do need generally to include 3-body interactions. And we will not really be talking today about how you get those interactions from QDC. That's another major topic, and one which there are probably better experts to present. The interaction we'll be dealing with today basically is a little bit less highbrow. It's derived simply from nucleon-nucleon scattering, then with so it's a 2-body interaction, and then, yeah, that's right. It's very hard to experimentally determine 3-body interactions. Have you ever tried to scatter 3 nucleons together at the same instant? two-body interaction from scattering with a few phase shifts that can be fit to unknown parameters that can be fit to, say, the binding energy of helium-4. So we will come over and over, though, to the point that, right, so even though we're using a potential to generate our basis functions, we're not actually assuming that potential, we're not actually physically using that potential later in our Hamiltonian. This is just defining our basis functions. In the end, the omega gives us our length parameter, which this time I've written out explicitly. Higher oscillator frequency, stiffer potential means narrower length parameter. Lower oscillator frequency means wider potential and wider wave functions. Okay, so again, scanning the width of our wave functions. You can have that visual picture. That was still one particle in 3 dimensions, but we're dealing with many particles. And thinking back to quantum mechanics, for a system of distinguishable particles, you can build the Hilbert space for the many-particle system just by taking all linear combinations of direct products of the basis states, of the single particle basis states. The simplest non-trivial example I could come up with was 2 particles, each of which having just 2 basis states, say spin down and spin up. Well, your general state for that 2-particle system would be any possible linear combination of the down times down state, the down times up state, the up times down state, and the up times up state. So in the end, your many-particle space would be 4-dimensional, and you'd therefore have a 4x4 Hamiltonian matrix and 4 coefficients to solve for in your eigenvectors. Unfortunately, we're dealing with A particles, and the single particle basis states are obtained by taking those 3-dimensional harmonic oscillator eigenstates, which, let's go back. The other thing to remember, I think you've seen the shell model already, at least in this course, is that 2n plus L gives you the major shell number that we group our states by. So the lowest shell has only L equals 0, but remember we then will have spin to couple onto that. So that gives us our 0s1/2 orbital. Our n equals 1 shell has angular momentum 1, that's why it's called the p shell, but then it can couple to spin either a 1 plus 1/2 or 1 minus 1/2. Then we have 2 and 0, and so on and so forth. So at the end, our basis states are n, L, coupled to j, and then an m projection. So those are our basis states, products of those. These would be, we have a bunch of coefficients for them. But there's the catch that, okay, these are fermions, so we actually take the anti-symmetrized combinations. Like for our 2-particle system, it would be states like this. So in the end, we're taking anti-symmetrized combinations over protons and neutrons separately, and we have to solve for those coefficients. So that's the quantum mechanical formalism. Any questions first? Yeah. So if you were, I mean, I guess ultimately, so it would be like the Triton or its isobaric analog. That's interesting. It seemed like you could probably, I could also imagine doing something like deuteron plus nucleon scattering. There might be things that you could do there. And those get into a very hard computational problem, but still actually manageable few-body problems. So yeah, I'd imagine you could. I don't know how, but I imagine you could. Okay. Yeah. So I imagine from a heavier nucleus, there's a lot of many-body stuff, so it gets messy, but maybe still. Okay, so the traditional shell model took these oscillator basis states and said, well, so in the traditional shell model, you basically said there are too many basis states for us to deal with. Let's assume that we just have particles free to move around in some valence shell, that the lower shells stay filled. But in that case, we have to use something different from the oscillator states. We have to come up with the most perfect ideal basis states for that valence shell, and then we'd work with those. So we'd use something like a Wood-Saxon potential or Hartree-Fock potential and work with those basis states. And actually, it's probably worth discussing a little bit more the shell model picture of collectivity. I think you've gotten some of this from Rick. The basic idea was, okay, now we have to introduce a mean field potential, and we're only looking at the residual interactions. And therefore, there are two regimes. Either we have a closed shell nucleus. That's when basically the matrix elements of the residual interaction are not large enough to promote a particle up to the next shell. And it's very hard to get collectivity in that case. But on the other hand, if we say we have an open shell, when basically there are orbitals that are closer together, some filled and some unfilled, closer than the energy that the residual interaction can induce in the particles. So we get some very complicated linear combination of configurations with particles in these different J shells, and that is what allows us to build up collectivity. In fact, in Monday's lecture, I believe you'll see how, for instance, the Elliott SU3 model builds up deformation in such a picture. Even in the valence space, dimensions can get really, really big. This is in the PF shell, looking by mid-shell in protons, and in neutrons, you're dealing with dimensions of 10 to the 8th. So it's a big challenge even to just deal with the valence shell. So we're going to do something even more ambitious, but we will therefore be constrained to very light nuclei, which is to say, let's forget about the shell model. There's something called the no-core shell model, which has been said to be more accurately called the no-core, no-shell, no model, because we are basically not going to assume a shell structure. We're just going to use those the original oscillator basis functions as a way to build our many-particle Hilbert space. We're not going to make any model assumption like that there is an inert core. So I guess this does not fit in with the conference poster. We have a bunch of models plus the ab initio approach from the summer school. But how does this work? There's the problem. So in principle, we can build up the full Hilbert space just by taking all possible combinations of distributing particles over oscillator shells. The problem is that's an infinite dimensional space. Same problem we saw with convergence on Monday in the geometric model. So we do have to impose a truncation, but it's a truncation which we will gradually relax and hopefully see our answer converging to the true result in the full space. Now, both since it makes sense, but also for some technical reasons, which maybe we can touch on in the informal discussion, it's natural to truncate by the so-called Nmax truncation, which is by the number of oscillator excitations. You basically start with 0 excitations. That would be the same as the shell model with all the particles in there, the traditional shell model, where particles fill up orbitals till you get to the valence shell. And that would be Nmax equals 0, no excitations. Then you consider moving in various particles up. Like here, we've moved 2 particles up, 2 shells, so we have 4 units of excitation total. This configuration would be included in an Nmax 4 or higher calculation. This looks simple, but when you consider all the different possible M substates of these shells, you realize that this is a very big combinatorial problem. This blows up very quickly. Let's see then how this works. Use this basis, do some calculations. In an ideal situation, so this is here helium-4, you would look, so this is as a function, each curve here is for a given Nmax truncation, like Nmax 4, what we have illustrated here. As you vary your oscillator parameter, you get different estimates for the ground state energy. Remember, we're working a truncated space, so the variational principle says that whatever wave function we have is going to be above the true ground, or at least not below the true ground state wave function in terms of its energy. There's some sweet spot when you choose the stretching of the basis functions just right. You get the variational minimum. But now you can say, well, let's add in some configurations with 6 quanta of excitation. Try diagonalizing for different basis length parameters again, and you'll get a lower curve, lower, and then you'll find yourself hitting rock bottom when you get to the true ground state, and this is beautiful. Independent of h bar omega, you've gotten the true ground state for this choice of interaction. I mean, this is always theory. That doesn't prove it's the true ground state in reality. But with this interaction, we've successfully solved the problem for the ground state, energy, and wave function. That's the ideal case, which basically is helium-4. In any real nuclei, the problem beyond helium-4 is a real nucleus, I know, but okay, in any more challenging nucleus, we basically don't quite get to convergence. This shows, for instance, beryllium-8 going up to Nmax 12 or so is about as far as we can get. And we're getting there, but this is still a pretty big scale. That's 10 MeV. We're not quite at convergence. And it gets worse as you go heavier. Yes? So helium-4, since you just have 4 particles, it's actually not bad. Even Nmax 16 was a small run. I mean, Nmax, up through Nmax 8 or 10, you can just do on a single core in a few minutes. I think Nmax 16, maybe I was getting up to, I don't remember, 120 cores for a few minutes. Beryllium-8, these were still not at the limit of complete horrendousness, these calculations. But this is getting up towards, right, the biggest calculations we're doing, so I should say all my work on the no-core shell model calculations like these is with the Iowa State Group with the code MFDN for any of you who are into that. Largest runs there are full machine runs on leadership class supercomputers for half a day. I mean, you basically, as far as you need as much computing power as you can get as you go to the heavier nuclei. So let's say 100,000 cores for half a day. The limitation is partly processing and partly memory. You need to store all these matrix elements, and you only have a gig. You can, well, in fact, this on the next slide we'll see. We'll come back to that question a little on the next slide. But first, I want to point out this looks all very pretty. You say, aha, we're converged. That was for the energy. There are other things we want to know about nuclei, other observables. Quadrupole moments, radii, transition rates. And some operators are very sensitive to certain details of the wave function, which may be converging more slowly. For instance, this is the Be2 in lithium-7 from one of the first excited states to the ground state. Actually, 2 different excited states to the ground state. As a function of Nmax, we're going to hire Nmax as a function of the length parameter. So can you pick the Be2 value off of that plot? So there's a bit of a reason for this, and some observables are better than this. Actually, like M1s would be perfectly converged. You just have a flat line. Their probable reason is that deformation is hard to build up, but also in a subtle way. We were using the harmonic oscillator basis, which falls off pretty sharply, like a Gauss. The harmonic oscillator potential rises to infinity, unlike the nuclear potential, which sort of flattens off. So that means the harmonic oscillator wave functions fall off more quickly. They fall off as a Gaussian, whereas the true single particle wave functions probably fall off more like an exponential. Tunneling into a flat region gives you a exponential. So basically, we're missing the tails of our wave functions. The E2 operator goes as R squared, so it heavily weights the tails of the wave function, and that is not a good combination. There may be ways around this. We're working on ways of extrapolating these results up to the true result, but there are big challenges here. And let's look at this. If we could get to infinitely large bases, it would be no problem. But, and this is what we were touching on before, the dimension of the many-body space grows combinatorially, both with the number of particles. So as you go from beryllium to oxygen to magnesium, let's say, and with how complete a basis we try to build, our truncation parameter, Nmax. So remember, Nmax 0, that's the number of excitation quanta here, is equivalent to the valence shell model. So at Nmax 0, we're still solving basically this valence shell model problem. With 12 carbon, that might be only 100, not so bad for the dimension. But as you go up, we have this combinatorial growth. The biggest matrices we can handle are about 10 to the 10th by 10 to the 10th. If you do the estimate there and say that's 10 to the 20th matrix elements and look at the memory of the largest supercomputer, you'll say there's no way we could handle a 10 to the 10th by 10 to the 10th matrix. The saving grace, any idea how we could handle a 10 to the 10th by 10 to the 10th matrix? Yeah.
Somehow not storage, but calculated.
So actually, that's right. There, on-the-fly calculation could help, definitely, and that is often done. And there's actually, then there's one other thing which really saves us even from having to calculate 10 to the...
These matrices, are they like a desert?
They are like a desert, yes. They are very sparse matrices. We have only a two-body or at most three-body interaction. This is actually part of the reason three-body interactions are more challenging to deal with than two-body. We have more matrix. Basically, a two-body interaction can only change the orbitals of two particles at a time. So that only can connect a very small subset of pairs of basis states. Three-body interactions can change three orbitals, so there are lots more interconnections between basis states and lots more matrix elements to deal with. Four-body is even progressively worse. All right, so with 10, we can handle basically at 12 carbon up to maybe N max 12 or so at best currently. Is that good enough? This is a very nice calculation with a schematic interaction, but a very nice one. If you're looking at some states in carbon 12, you might say excitation energies are actually pretty good, 0, 2, 4, 6, 8 for our Nmax, and hey, the excitation energies are pretty stable. But there's a very famous state in 12 carbon, which if you're an astrophysicist, you probably know about. Have you heard, how many of you have heard of the Hoyle state? Yeah, okay, it's pretty well known. It was actually predicted from the fact that nuclear reactions gone in stars that there had to be a Hoyle state before it was so low-lying 0+ resonance before it was actually discovered. And do we get it? Here's experiment. Do we see any state like that in the calculations?
Can you enlighten us what's that state?
Oh, it's basically it's a triple alpha clustering state. 0+ state at about a little bit below 10 MeV in 12 carbon. Was that what you were asking? Or? Okay, yeah. Okay, so at 4H bar omega, there's some very high lying. So the issue is building up cluster correlations in these oscillator basis functions. 4H bar omega, there's a state way up here. 6H bar omega, it's plummeted down. You can imagine that by about 20 or H bar omega, and you can actually come up with more precise estimates of that, it should be converged. But we aren't getting to 20 H bar omega anytime soon, so we have challenges converging some states even, getting them to even exist in the calculation, as well as getting those long-range observables. One approach to this is to try to build better bases. Can we find some physically relevant subspace in advance, rather than just building all these Slater determinants, building the Hamiltonian, and crunching away? We'll discuss a little bit later, since this does tie into collectivity and rotation, the very elegant SU3 approach that Tomasz Dittrich and the LSU group, Louisiana State University group, have been developing. There are other approaches. Physically adapted radial bases might help with some of those asymptotics problems. There's an approach called importance truncation that tries to, on the fly, determine which basis states are most important. So there are approaches. On the other hand, today we are going to just be looking at plain old no-core shell model calculations for the first part of the talk, and see that despite all these challenges, we can still see collective behavior emerging. So actually first, we're about to transition to rotation. So are there any other questions bubbling up, or comments or ideas? Yeah?
So what is now the record of the largest nucleus calculated with ab initio method?
So I should say I'm focusing today on the no-core shell model, but there are, just because there's only so much we can cover in one day, there are other models like Green's function Monte Carlo, coupled cluster. So from the no-core shell model, let's say oxygen 16 is the typical high end of normal nuclei to cover, but there have been some proof of principle calculations up higher. Coupled cluster approach is a bit different. It can fairly easily, in certain truncation schemes, reach up to much higher, but only for nuclei that are doubly magic, or at least close to closed cores. Green's function Monte Carlo tends to be limited more to about A = 10 or 12, but has its own strengths. Okay. So, rotational model. This is why rotational models are useful, because there's this much more so than the schematic forms where you said, if you're axially symmetric, you can only have a k equals 0 band, is basically what we saw in the ideal rotor on Monday. But in general, instead, you have some sort of intrinsic wave function going on. So a rotational state is one where you have a separation of degrees of freedom. You have some sort of intrinsic wave function, which we are schematically describing by this ellipsoid here. You could say if that ellipsoid were fixed, what would the particles be doing inside it? And then you convolute that with a rotational motion. And there's this symmetry constraint, because if you turn the nucleus end over end, if it's axially symmetric, you should get basically the same state. Okay, so you have one basic property, the k quantum number. Again, we're dealing with axially symmetric rotors in this discussion. That's because if you have an axially symmetric situation, the angular momentum around that symmetry axis, the projection onto that symmetry axis, will be a good quantum number. That's our k here. And all right, we have some consequences of having a wave function of this form. So the idea is, okay, again, so the thing is, you take the intrinsic wave function, rotate it by certain Euler angles, and the amplitude for that is given by the d function. That's the formal structure. The kinetic and the rotational energy coming out of this will be going as j plus 1. And when we're analyzing such states, plotting E versus, so if you plot E versus J, you'd get a parabola. A parabola is sort of hard to recognize versus some other shape that also curves upwards. So for analysis, it actually makes much more sense to plot versus j plus 1, since then you should get a straight line with slope A and intercept E naught. That is true for most k values, but for k equals 1, there's a cross term in the Hamiltonian, which gives you a staggering between the alternate angular momenta. So you will get something that looks a bit more like this. That's basically the Coriolis interaction, the Coriolis term in the kinetic energy. All right, those are energies. And in fact, this, by the way, was the textbook that I recommended on Monday. Very nice introductory. The introductory chapter of this textbook is free on the web, a very nice overview of many aspects of nuclear structure. So I do recommend that you just Google this and download the introductory chapter. And you can use it for reading on your flight back, except those of you who are going on ground, and then don't read it if you're driving. So here would be a perfect rotor. I think you've seen some of these, a very nice rotor. I think you've seen some of these in your other talks. You have the various K bands. That's an even nucleus. Here's what happens if you plot energy versus j plus 1, and you get these pretty close to straight lines. Notice that you do have some differences in slopes. That's one of the things we want to be able to predict and understand, the slope parameter, basically the moment of inertia of the band. Here is an odd mass nucleus, which I point out because you can see a k equals a half band has that funny business with the Coriolis term going on. Instead of this nice j plus 1 smooth progression, notice what's happened. The 1/2 has been pushed up above, well, things are just completely staggered around here and also here. It's very hard to even tell without carefully plotting what's going on. And this does rotational behavior. It goes on across the nuclear chart from 8 beryllium, which we'll be discussing today, to up to the actinides. With very different energy scales as we build up larger nuclei, larger deformations, and higher moments of inertia. So we're talking about many MeV energy scales here in the light nuclei. All right, those were energies. Actually, we can pause and see if there are any thoughts or questions first just on the energies. All right, now, though if you've already seen, like in Rick's talk, a discussion of the Alaga rules, you know that some of the most important signatures of rotation actually have not so much to do with the rotational states themselves, but of the relations between them. In fact, that's an important point. the way we will, so pardon my skipping back, the way we will recognize these wave functions is by the relation this implies between the different states in the band. Not just the energy, but the fact that they share the same intrinsic state. That gives us relations on the electromagnetic matrix elements. Those are the Alago rules. Microscopically, let's review, or this may be the first time you're seeing it, what the multipole operators are. So the quadrupole operators basically take this Y2 spherical harmonic tensor and multiply by R squared and sum it up over the particles. This would be a nice operator, except that different particles have different charges. So this actually breaks up. We have two classes of identical particles, the protons and the neutrons. So we really have a linear combination of a quadrupole operator for the protons and one for the neutrons. Now, actually, this will probably, to most people, this would sound like a strange way of saying things, because we all know that the proton is charged and the neutron is not, so we just are looking at the protons. We will come back to this later, though. It's actually useful to also look at the neutron quadrupole operator, and so I'm actually flagging it here. Then we also have the other operator we're going to be looking at is the magnetic dipole operator. That really just is a sum of the angular momentum operators, both orbital and spin, for the different nucleons, with a certain weighting. So the electromagnetic M1 operator involves this weighting that has to do with the G factors of the nucleons. You have the proton is charged, G factor of 1. The proton spin, though, has some different G factor. The neutron's uncharged, so its orbital angular momentum, its motion doesn't contribute at all to the M1 operator, but its spin does. This is a pretty odd linear combination. We can actually deduce a lot more about the structure if we look at each of these spin contributions and angular momentum contributions separately. These are called dipole terms. So again, we'll come back to this. What are the relations? The rotational relations basically tell you that within a band, the reduced matrix elements of the quadrupole operator will be just proportional. Their dependence on which band member, what J's we're talking about, will just go as a Clebsch-Gordan coefficient, times one constant overall factor that depends just on basically the quadrupole moment of that intrinsic state, that gray ellipsoid for that band. These reduced matrix elements give us the quadrupole moments, and then also the BE2s if we're talking about the reduced matrix elements between different states. And again, this point, so the prediction, so depending on K, you can plot out what these Clebsch-Gordan coefficients are. For K equals 0 band, you'd have these quadrupole moments as a ratio to the intrinsic quadrupole moment, the intrinsic matrix element. Again, the transitions would be proportional to that same intrinsic matrix element. You have delta J equals 2 transitions. The quadrupole operator is a spherical tensor of rank 2, so it can couple states with angular momentum differing by 2. You get these curves. You have delta J equals 1 transitions. Depending on K, you get these curves. And these are pretty firm predictions. So if we have rotational states, the moments and transitions should follow those patterns. And as I was starting to point out, we are, and I'm allowed to say this since I was an experimentalist, theorists have a big advantage over experimentalists, which is that experimentalists can only measure things that can be measured, right? It's this thing that, like, protons are charged, neutrons are not. So they can only measure the proton properties, so the E2 operator. Well, we can just look at the neutron E2 operator just fine. We have our wave functions. We can calculate it. Actually, I'm not quite being fair, because there are some ways experimentalists can get at the mass quadrupole moment or mass quadrupole tensor, which is the sum of the proton and neutron quadrupole tensors. So they have a little bit of a handle on that. But okay, so right, so we can look separately at proton and neutron tensors and see if both of them follow the rotational relations. The operators have the same operator structure, so all these Alago rules should apply to the matrix elements of both of them. Magnetic dipole matrix elements you can break into, so we got into a little bit of a model here. The traditional approach breaks the operator up into a contribution from some rotational core. So I'm not talking about a spherical core here, but some basic rotor that then is loosely coupled, or perhaps to some extra particle. We'll see a more concrete example of this later. In that case, the core contribution has a fairly simple form. It's going, this is the reduced matrix element of the angular momentum operator, which you can look up. Since the matrix elements of the angular momentum operator are just given by those good old relations, you know, j plus or minus acting on some state is square root of j plus or minus whatever. So there's a simple formula for this, which you can look up, where it's in the preprint. And then you have some contribution from those extra particles outside the core. Here, again, it gets messy. They go as Clebsch-Gordon coefficients. But there is a cross term that arises in the case of k equals a half bands. So a little bit of messiness to deal with, but we can handle that. The basic thing is each of those three terms has a fairly simple dependence on j. This core contribution can only contribute to dipole moments, and it just gives us a linear contribution. This main term, the direct term, has a fairly smooth behavior, flat for the dipole moments. In terms of transitions, there are only delta j equals 1 transitions, since the M1 operator is rank 1. And those again have a fairly smooth behavior. It depends on what k is. And then, easy enough to remember, the cross term, just like the Coriolis term for the energies, the cross term here gives us some sort of staggering behavior. So we'll get some superposition of those. We have only 3 parameters to deal with, even in the case of a k equals half band, and lots of dipole moments and transitions to explain with just 2 or 3 parameters. And again, being theorists, we can look at the dipole moments you would get if the only contribution were from the proton angular momentum, or from the proton spin, which will probe a very different aspect of the structure, or neutron orbital angular momentum, or neutron spin. I think that's it for the rotational formalism before we start plunging into calculations. So this is all written out in excruciating detail. Oh, and I should say the exercises today will be, you will get to reproduce, you'll get to play with convergence in the core shell model to get a little bit more of a concrete feel for it, and then reproduce some of this rotational analysis. 2 catches there. You will not be running 10,000 core jobs on a supercomputer today. I think Guillaume would have a fit if we tried running those on the Talent server. So I actually did runs in advance, and you'll have data files, and you'll get to see just how cross-eyed you get looking at data files, which I'm sure many of you have already experienced. And what's the other aspect? Oh, the other aspect is everything in the paper was done, you know, theorists have it lucky. We can turn the Coulomb interaction off if we want to. Oh yeah, I don't want particles to be charged today. The advantage to that is it makes isospin exactly conserved, which makes it a little bit easier to analyze your spectra. As Pete pointed out, and the Coulomb interaction tends to just shift some energies without really affecting the structure. I've given you calculations today with the Coulomb interaction turned on, so you can compare with the paper and explore the difference you get there. When you get the handout for the exercises, you'll see that there were too many fun exercises, so I gave you more than you can actually do. I tell you to have fun and basically pick which ones are most interesting, but if you're ever enthusiastic afterwards, you can finish them off on your own. Yes? I'm sorry, the indices of... So it's a rank 1 tensor. This is the k equals 0 component of it. This is k equals 1, which connects the k equals plus a half and k equals minus a half substates. The bar here means the conjugate state under rotation by 180 degrees, under flipping the z-axis. So this has actually k equals minus a half.
It should be, I guess, 1, 0 and 1, 1, right? In the Clebsch-Gordon coefficient.
Did I do something? Oh, that too should be a 1. Yes, thank you. Somebody can remind me afterwards to fix my slide. I can write it down. I can remember. Mallory, you can send me an email afterwards reminding me to fix my slide. Thank you. Yes.
Is there any good way to identify the best basis to make our calculations? I noticed that in one of your slides you show a SU3 symmetry basis.
We will actually talk a bit about that in the second half of the talk, and that actually can potentially make big improvements. Yeah.
Should be possible another basis?
Yeah. I'm sorry,
Should
possible
be possible propose another basis?
to propose another basis?
Yes.
Within the SU3 context, there's the idea of a symplectic basis, which we will touch on lightly. I have spent a lot of time, well, one of my pet projects, this is another paper where I actually put in a lot of introductory materials, so I should probably give you a reference. Okay, if you search on arXiv, nuclear theory, Caprio, and look for the word Coulomb in the title, Coulomb-Sturmian, you'll find another paper which deals with a lot of shell model details, including this idea of alternative radial bases. So let me write this down, if you would like it. Coulomb-Sturmian Caprio. That's one particular basis, but the discussion there actually applies to how you would deal with general bases in the no-core shell model. And then also you can search for some papers by, here's another one which comes to mind, Robert Roth on importance truncation. And there are probably a bunch of others that I am not coming up with offhand, but that can give you some basic starting points to look at. You're welcome. Okay, so let us look at some of these comparisons. I have to say, yes? I had a wonderful so there are a couple of things going on. The R square, I look more at the R, for technical reasons, which I can discuss, I've looked more at the R squared operator first, which has pretty similar behaviors. I hope that there would be wonderful improvements in my initial calculations. It looks sort of the same. That's actually not necessarily conclusive, though. There are a lot more things to look at in terms of... So there's a problem. These light nuclei I'm looking at, helium, like lithium-6, are basically a helium core, which actually is one of the few instances where you have something that really does look like oscillator wave functions. It's so tightly bound. And then some extra neutrons floating outside. So if you move to some wave functions with beautiful asymptotics and optimize them for those neutrons floating outside, you're having trouble with the core. So there probably are better optimizations that can be done. I've already done some calculations. They don't exist out there anywhere yet, but with, say, using the oscillator function still for the protons, which are all sitting in the core, using Coulomb-Sturmian for the neutrons. I think to actually have a real hope of working, you probably have to use a hybrid basis, for those nuclei at least, one which includes some oscillator-like functions for the core nucleons and some ones with nice tails for the halo nucleons. Yeah, so I would have been happy if the first calculations turned out and beautifully solved everything, but things never work out that way. It was still with GIST, yeah. Okay, so electromagnetic. So I must say I was somewhat amazed the first time I saw these results. The idea here is, remember we have, once we've normalized the quadrupole, one number, the quadrupole moment, intrinsic quadrupole moment we're free to choose. For simplicity, we just chose that to get here, we said, let's choose that to get the quadrupole moment of the, oh, so I should have, yeah, sorry, I'm jumping way, I missed a slide here. Stepping back, what nuclei are we dealing with? Beryllium isotopes. Why these? These are the lightest ones that actually start really showing rotational behavior. Helium-4, there's not too much you can say about, for instance. What do we have here? On the left, we have the odd mass isotopes. On the right, we have the even mass isotopes. We've just taken all the levels from the no-core shell model, just 16 interaction calculation. we've said, oh, these values are not converged, but we can take a snapshot at some given Nmax, some given h bar omega for our basis, and see what comes out. There's another aspect. Nuclear force conserves parity, more or less. You can split that. It certainly does with our theoretical interactions. You can split the space problem up into the so-called natural parity space, the one that you get with the lowest filling of oscillator shells. Right, so each oscillator shell has alternate parity to the one below it. If you promote a particle by one oscillator shell, that reverses your parity. So you can choose your basis to only have states with even number of oscillator excitations, starting with 0. That's what we call natural parity. We can play with this on the blackboard in the discussion session if you'd like. Or the unnatural parity states, which for these nuclei are positive parity, are also pretty low in energy, so we can look at those. All right, so these are our levels, plotted versus JJ plus 1 to see if we can recognize rotational bands. And what I've drawn here, I filled in as black dots the things that look like they might be part of bands. This is based not only on the energies, but when we delve a little bit deeper into the electromagnetic transition strengths. Then the lines are just fits with rotational formula to see how close to rotational these are. So for everything but k equals a half bands, the fits will just be straight lines. And we can see a few different behaviors going on. There are some cases where we see a band that just stops. And the dashed line here actually indicates if all your particles were confined to the valence shell. Traditional shell model, or Nmax equals 0 in the case of the no-core shell model, what would be the maximum angular momentum you can build out of those particles? And so we see that some bands look beautiful. This is 9 beryllium. 9 beryllium will be our toy case for the rest of the day today. 9 beryllium, you have an ERAS band, it looks like, that's beautiful in energies and then just cuts off. There's no next state here at the valence angular momentum. You have some bands where it turns out that there actually are states that still look somewhat like band members when you look at them in detail. But something funny happens at this valence angular momentum cutoff. And these are all things I don't pretend to have deep answers for. These are just things that are popping out of the data and that we need to understand. And then you have some bands which seem to just plow straight on through the valence angular momentum cutoff. We will pick two examples here, 9 beryllium natural parity and 9 beryllium unnatural parity, to look at in a little bit more detail as our examples. So let's start with 9 beryllium natural parity ERAS band. So that's a k equals 3/2 band. And so as we're starting to say, if you plot the quadrupole moments, you have one normalization point. That will be different for the protons and neutrons. So we've normalized the proton quadrupole moments and the neutron quadrupole moments independently because there's no reason to expect them to be the same. We have one more neutron than we have protons. And it's actually bearing in mind that if you pick random pairs of states, their quadrupole moments are differing by orders of magnitude. Quadrupole moments are signed quantities, so they're flipping in sign. Out of a few orders of magnitude, being within about 10% is actually pretty amazing to me. We can also see that we don't have perfect rotational patterns here. Look especially at the neutron quadrupole moment. That one's quite a bit off from rotational. The question maybe is not so much why does it deviate, although that's actually going to be our handle on understanding the physics further probably, but also why should an axially symmetric, pure rotational adiabatic separation picture even begin to work for these nuclei? Then we do get something funny happening with that highest band member. I mean, that doesn't look like a very happy camper to me. Now let's look over at the E2 strengths. Oh, this is the other advantage theorists have over experimentalists. Experimentalists can usually only measure transition strengths, which are squared matrix elements. But the signs actually have some meaning. You have to be careful. It's spelled out, again, in excruciating detail in the preprint. But they're actually signs that can be checked here. So let's look just at the matrix elements, not their square. The solid lines here are predictions based on that first quadrupole moment there. So the fact that those points happen to lie up against the line is not because we fitted it, it's because they just happen to land there. And you can see again things get a little bit iffy when you get to the highest band member, but still this is looking suspiciously like a rotational pattern of some sort. That's not telling us what the intrinsic state is, but it is suggestive that we have this rotational separation. And again, what we have done here is we've just put a bunch of nucleons into space, thrown the Schrodinger equation at them, and we have this type of stuff coming out. Dipole moments. Again, we have the 4 different dipole terms, the 2 different protons and neutrons, orbital versus spin. And as you might expect, those are very different operators, so you get very different behaviors. So to actually interpret these, it's worth, so I can say there's a lot I can't interpret about this, cannot interpret about this, but it's useful to at least have as a baseline the classic picture of beryllium-9. So what would you expect beryllium-9 to be? Beryllium-8's ground state is known to look more or less like 2 alpha particles. So you have 4 protons, 4 neutrons, but they break up into 2 alpha particles, which are actually not even quite bound. It's just a resonance state. Beryllium-9, then you're adding 1 neutron to that system. Its ground state actually is bound, and that neutron is presumed to act sort of like the covalent bonding electron between 2 atoms in a diatomic molecule. So you have this neutron sort of loosely bound to those 2 alpha cores and helping to hold them together. So in a picture like that, what would your, again, there's this idea of separating the nucleus into a rotation, for the purpose of M1s, separating it into a rotational core, and then the extra core nucleons. You'd think, well, maybe the beryllium-8 would be the core, and then the extra nucleon would be the extra particle. So you'd expect, well, the core would have both orbital motion of protons, from the protons and those alpha particles, orbital motion of neutrons, which would be similar, but a bit different since you also have the extra neutron. Maybe it's not really separate. Well, in any case, it'll give something to them intrinsic contribution. So the straight line contributions you might expect to be pretty similar, but with some extra intrinsic contribution. That could sort of fit this. When you look closely at it, the picture breaks down a little. But in any case, the orbital parts would come from the core predominantly, and you do see the straight line that you expect from core rotation. On the other hand, if you look at the spin contributions, well, the spins are going to be paired to 0 for the nucleons within the core. So all the protons are paired to 0. We should not be getting any spin contribution from the protons, and that's basically the case, flat line down here. But the neutron there is that extra unpaired neutron. Its spin is in play, but that would be mainly coming out of those single particle terms, not the core terms. So we'd expect one of those, if you look back to those plots, the direct term of the single particle part, or the extra core part, gives us something that looks pretty flat, which is what we see here. So there are basically, again, 2 parameters in each of these curves, and those same 2 numbers enter into the predictions over here. These are the magnetic transitions, and we are pretty close to spot on, except again for that rebellious J equals 9/2 band terminating state. So if you have the enthusiasm later today, you will get to recreate the analysis like this. So actually, before I leave this, were there any questions, like which are triangles and which are circles, or more profound things? I mean, this was really a funny experience to me. Again, you remember that I was Rick Caston's graduate student, and I got courses very similar to yours. So for me, doing rotational analysis of odd spin nuclei was, actually you'll be getting this when he does the Nilsson model this coming week, was like tungsten nuclei. Mass is approaching 200. So it was really funny to be suddenly trying to dust off those memories and applying it to nuclei down around mass 8. Okay. So our other example, let's take an example that goes to a higher angular momentum. Actually, you'll notice a pattern. The unnatural parity spaces, even the valence space goes up to much higher angular momentum, and that's natural because, or unnatural as it were, because you've promoted a particle out of one shell into the next higher shell. That higher shell contains higher J orbitals, and also, as you discovered from the M scheme, when you have particles in the same orbitals, the Pauli principle prevents some restrictions on the angular momenta you can build, whereas when you have particles in different orbitals, there are no restrictions on the angular momenta you can combine them to, so promoting a particle to the next shell also removes some Pauli principle constraints. So in these unnatural parity spaces, we've gone from being able to, in beryllium 9, for instance, we've gone from being able to get 9 halves for the spin up to 13 halves, so we might expect that bands could proceed a little bit further. So let's look at that ERAST band. Again, notice the energies get wifty above the valence cutoff. If you look at the quadrupole moments, again, black squares are for proton quadrupole moments, open squares are for neutron quadrupole moments. We have, again, just one normalization point among all of these. It's following the pattern pretty well. There clearly is something going on. And then even those last two states, which looked way off in energy, you probably would have said, those states, are they really part of that band? You must be kidding me. You're seeing bands where they don't exist. Actually, the quadrupole moments are not too bad, but yeah, they're off by a factor of, 50% or so. When you come up to the transitions, remember, they're even free signs here. They are almost spot on, somewhat miraculously. If you look at the dipole moments, again, these are all over the place for states that are not band members. You again see this is pretty consistent with the rotational pattern. Obviously, there are some deviations. And then remember, once we've fixed our parameters for each different dipole operator within this band, it's one set of parameters governing both the transitions and the moments. And that's not terribly bad, for instance, for those triangles. So I would say something clearly rotational is going on, but we still have to understand the structure. Why is this slide here? Yes, okay. We saw this slide before, and it's time to come back for a reality check. I think I hopefully successfully convinced you at the beginning that we are in a completely impossible situation because, for instance, collectivity is measured by E2 transitions, as you've had drummed into your head over the course of this week. And our E2 transitions were completely unconverged. We couldn't look at the plot and even begin to guess what the E2 strength was. And then suddenly we were seeing rotational patterns coming out as if we had perfectly converged transitions. So the point is, and what were we doing? We were just taking a snapshot of all our transitions at basically h bar omega equals 20 or so, and some particular n max, which wasn't even a terribly high one. And we saw rotational ratios popping out. So either we were hallucinating or something else is going on. And the something else that's going on, we may be hallucinating and then convincing ourselves that's correct. But no, seriously, the other thing that is going on is that even though convergence is not there yet, relative properties are converging a lot faster than absolute properties, especially for states within the same band, it seems to be, which implies that their intrinsic structure is somehow converging. You have basically the same intrinsic state, just some different details of how it's tumbling over itself with rotation, and so that intrinsic states convergence seems to be pretty consistent among the different states, despite their slightly different rotational motion. So let's look at this concretely. Energies first. Remember, when we're diagonalizing the Hamiltonian here, the energy of what happens if you put all these particles and hit them with the Hamiltonian, this is basically the binding energy of the system. The energy eigenvalue is the binding energy, so it's some big negative MeV number. If we do an Nmax6 calculation, here are those first two bands in beryllium 9. This is the natural parity space. This is the unnatural parity space. Okay, we get some energies. Let's go to Nmax8. We get some quite different energies, down by a few MeV. Go to Nmax10. Well, we don't get as much more energy, but still going down by a couple of MeV, not converged. But what if we notice that the relative energies within the band actually seem to be staying pretty constant? It's the band as a whole that's moving down. Let's replay that. Band as a whole is moving down. So what if we look at excitation energies relative to the ground state? Let's do that separately for the natural parity space. Call this the ground state. Unnatural parity, let's call that the ground state. And you see things are a lot more stable. Still, there's some motion of the two bands relative to each other. And some of these other states are moving at very different rates. But within the band, things are actually quite stable. All right, what about the matrix elements? So absolute E2s are not converged. Let's not even show that again. I think we convinced ourselves of that. But these relative E2s, so when we normalize the first quadrupole moment, you can look at, if you do Nmax 6, 8, or 10, how that changes. Well, a normalization point, of course, stays fixed. That's just by definition. But even these points are quite stable. Higher up in the band, things are a little bit less stable, but the change from Nmax 6 to Nmax 10 is still within the realm of being recognizably rotational. You might want to be, okay. Same holds for unnatural parity. All right, for the dipole moments, I think the big difference is that a dipole operator doesn't have any pesky factor of r squared in it, so it's not as sensitive to the tails of the wave functions, so it has a better shot of converging. These are basically converged on absolute scale here. That divided by mu n, those are just the units. That's not some normalization. That's not some variable normalization. Okay, so enough said about M1s. Pretty stable with Nmax. It's still, despite my saying that the quadrupole, absolute normalization of the quadrupole, intrinsic quadrupole moments is a lost cause, there actually is a little bit more we can learn from looking at them. We have these two operators. So as a reminder, how are we getting these intrinsic quadrupole moments? I've just said, take the quadrupole moment of the lowest band member and figure out what that would, to divide out the Clebsch-Gordon coefficient and see what you'd get for the intrinsic quadrupole moment. You do that for the protons, you do that for the neutrons. This is a scatter plot showing what happens for each band. So like the ground state band of beryllium-9, the excited band of beryllium-9, and then over here we have the unnatural ERAS band. What happens as we increase Nmax? This is Nmax 6, 8, and 10. So clearly the quadrupole moment is not converged. It's still moving pretty rapidly. Who knows where it will end up? But it's moving more or less straight out from the origin. That means that the proton and neutron quadrupole moments are staying in pretty much the same ratio as our states converge. That already can tell us something about the state. This, for instance, in the unnatural parity state, it looks like the neutrons have a much bigger quadrupole moment than the protons do, whereas that isn't the case in most of these ERAS bands, where if anything, the protons have a slightly bigger quadrupole moment. And even though these are still growing, that means that the true value is probably somewhere up here. And did Rick discuss Weisskopf units?
I think Carsten mentioned them at some point.
Okay. So, and again, on the principle of anything that you might ever want to know, stick of in an appendix of the paper. You do have some discussion of Weisskopf units also in the appendix of this paper. Oh, and also the appendix of my thesis. So you have plenty of appendices to deal with. It's basically the assumption that if only one particle were contributing to a matrix element, then you can do an order of magnitude estimate of the matrix element by saying how big is the nucleus. That's a little bit hard to say for these light nuclei. You all know the R to so R goes as A to the 1/3 rule for nuclear radii, right? That may not quite apply for these light nuclei, where instead they're all sitting in a nice little sphere. You might have two alpha particles loosely bound to each other, but it's probably in the right ballpark. So you can just ask, okay, if you had a single particle floating around in a sphere that size, what would be the estimate you'd get for the size of a matrix element? We can compare that to the intrinsic matrix element that we're getting for these bands, and we're seeing that whatever the true value is once we converge, it's somewhere up significantly larger than one Weisskopf unit, which would be these gray bands. So that in itself, I guess, is a little bit interesting. Okay. we're going to move on to trying a little bit more speculatively to understand some possibilities of what might be going on here with the intrinsic structure, but this is probably another good point to break for questions, like on these convergence issues.
What is the number indicated in the figure?
Oh yeah, so let me spell out the numbers. The number on each curve here is the mass of the isotopes. These are the beryllium-9 bands, these are the beryllium-11 bands, beryllium-10. Circles here are the natural parity bands. So the ERAS natural parity bands all cluster in this cluster. The red ones are the excited bands, and the black ones are unnatural parities. They're over here. The 7 and 12 here are, the Weisskopf estimate depends on how big a sphere you're assuming the nucleus is by the classic formula. So that will get a bit larger as you go from A equals 7 to A equals 10. I think that's it. Okay.
Okay, so what have you shown us with these things? Something yes, something no. For example, you can get not the absolute energy, but you can get the
Ratio,
the
yeah,
ratios.
yeah.
What do you mean by here, ratios of P and N?
Oh, sorry. The ratio, I should probably have said the ratio of the P to the N moment. It's the idea that even though the neutron moment is changing as we go along here, even though the proton moment is changing, they're staying. The ratio looks, we can try to, a line out from the origin would be, oh, can we do this? Would be like that. So it's sort of along a straight line out from the origin if I'm not fudging it with my hand. I really wanted to get it, no, I'm not going to be able to do that. Okay. Yeah, the low tech, that's a good point. Okay. The stick might be curved, you know, though. Okay, so, yeah, any other questions? Yeah. This is purely, I mean, we really just are setting the charge equal to 1. So no effective charges. Again, the no-core-shell model in general, since we don't have any inert core, we would not really have any justification for having an effective charge. There are, so we don't here, that does raise the interesting issue. We're working in a truncated space. Even though we're not truncating from the bottom, we haven't insisted on any closed cores. Well, I guess we sort of are. We're truncating by Nmax, so there are approaches. The so-called Lee-Suzuki method, for instance, was for a while at least used very regularly in the no-core shell model, not in these calculations, as a way of trying to come up with effective Hamiltonian operators and then also, in principle, effective transition operators in a sort of well-established, formalized way from the truncation process. So there can be effective operators in that sense, but not here. Any other questions?
Two questions. What is the interaction being used?
This was the GIF16 interaction. It's the two-body interaction deduced from scattering and then with some phase shifts fit to binding energies of a couple of the light nuclei. The 16 actually means binding energies of certain nuclei up to mass 16.
And the second one is the relative convergence of the low and higher spins the same?
That is actually probably one of the most interesting things. One of the biggest questions I have actually is, so there are a lot, even at the same spin, there are a lot of differences, let's look here, between, say, members of these two bands and some of the background states. Let's run this animation back and forth a few times. You're seeing a big motion, it's sort of hard to tell just from looking at this, but there are differences in convergence from different states, even at the same spin. And then, if you look at, within the band, at the valence cutoff, there seems to be a difference in convergence rate above and below. I don't know if we can see that so much here. Those states were moving down a lot more quickly. That jump is a lot bigger than that jump, for instance. So it is entirely possible that by Nmax 20, those states would have actually caught up and be lying on that curve. They might even have overshot, and you might get some higher lying band that crosses, and really funny things could potentially be happening. There's still big questions about the subtleties of the convergence there, and why the valence cutoff seems to be so important for it. So, okay, so let us ask the question then of, we've mostly been looking at individual states and then seeing if they fit into the rotational pattern. But now we'll look a little bit more at these bands as a whole and try to get some hints, they will only be hints, as to the intrinsic structure, right? Because seeing a rotational pattern just tells us that what we're seeing is consistent with an adiabatic separation into D functions, giving us tumbling motion in the Euler angles, and an intrinsic wave function. It doesn't tell us anything about what that intrinsic wave function is. The first observable we're looking at that had some relevance to that was that ratio of the proton to neutron quadrupole moments. That tells us something about the proton and neutron distributions within our intrinsic state. So the next thing here is going to be a little bit speculative, but an interesting comparison to what there are so-called molecular dynamics approaches which naturally build cluster structure. And those have been used for the same nuclei. So actually three things we're comparing here. On the left, we have the no-core shell model calculations. We're looking at two of the even mass nuclei here. So you have in both these nuclei, you have a ground state k equals 0 band, which ends at the maximum valence angular momentum. I mean, it's a little bit of a stretch to call a 0 plus and a 2 plus state a band, but maybe in some sense. And then you have an Erare band, that's a fun word, off Erast band, which plows right on through the valence cutoff. The other thing to notice, though, when you look at these bands, is notice the difference in slopes. The excited band, how is its slope compared to the lower band? Steeper? Shallower? Shallower by about what factor? Something like, yeah, it's hard to judge just from looking at the plot. It's about a factor of 2, maybe shallower. So very different moment of inertia if you interpret this as some sort of rotation with a moment of inertia. Bigger moment of inertia to have a shallower slope. Let's look at experiment. There is some experiment floating around. Experimentalists, again, have a hard time. Unlike most of those other rotational bands you've seen, most of the states in these bands are resonant states. So you have widths to deal with. You have all sorts of challenges in observing them. But these are experiments on the same nuclei, beryllium-10, beryllium-12, which again saw an Erast band and an excited band, where, voila, the excited band has about a factor of 2 lower slope, again, roughly speaking, than the Erast band. And the molecular dynamics people, so there's a little bit of a hybrid here. We then have superposed on this the molecular dynamics interpretation, had an interpretation, at least for beryllium-10. So there are two different interpretations going on, and they actually are compatible with each other. One is that this lower band is more of a traditional shell model structure, and that explains why it would terminate at the valence angular momentum, whereas the excited band is more of a diatomic, a dimer structure, two clusters bound to each other. That could be something like helium-6 plus helium-6 here, or you could imagine having extra neutrons floating around as well in smaller cores, smaller clusters. Then you have a picture which comes out of the molecular dynamics calculations, which goes back to the idea, at least for beryllium-10, that you have a beryllium-8 core, 2 alpha particles strongly bound, and then here for beryllium-10, we'd have 2 extra neutrons floating around as the covalent bonds between the quote-unquote atoms of the dimer. And there are different types of orbitals they can be in. They can be in so-called pi orbitals, where basically the lobes of the orbitals extend out to the sides. Or they can be in so-called sigma orbitals. Those are based on angular moment, which Legendre polynomials, L equals 1 or L equals 0 Legendre polynomials describe it. And those would have lobes extending out the ends, which, because neutrons floating out past the ends will increase the moment of inertia fairly significantly. And you get basically exactly these predictions of a ground state band that's pi orbitals, an excited band which is sigma orbitals, and therefore a much larger moment of inertia, shallower slope. And these are not incompatible, since when the cluster people look at it, the pi orbitals you can actually reproduce pretty well in the valence space. The sigma orbitals need many h-bar, so many, it's a bad terminology, many oscillator quanta of excitation in your basis. So basically, you need the no-core shell model to get sigma orbitals if you want to reproduce them, the states, whereas you wouldn't so much for the pi orbitals. So this is certainly one possible interpretation of what might actually be coming out of our no-core shell model calculations. All right, we have these giant wave functions here. We have to start, you can get the eigenvalues, you can get the eigenvectors, you can start looking at operators to try to decipher it, but it's not that you can just print out this wave function and immediately see, aha, I have some sigma orbitals and a cluster structure going in here. This would be, I think, a big challenge going forward, being an experimentalist on theory calculations, right? Taking these calculations and extracting some structural information from them beyond just the raw numerical prediction. I mean, obviously, raw numerical predictions are great. If you're predicting an astrophysical reaction rate, you don't actually care necessarily what structure it comes from as long as you get it right. So there's that merit just to getting the right answer. And then, though, if you want to understand it, we may have to be a little bit clever. So we're almost at the end of this part of the talk. This last slide then gets a little bit speculative. If we wanted to start comparing with experiment, what would you want if you were an experimentalist thinking about a rotational band? What are some of the basic properties? We've said, aha, we get pure rotation. The experimentalist, if we're lucky, might measure those states and say we have pure rotation. Is that the end of the story, or is there more we should be predicting? Well, we at least have those band parameters. Remember, for each band, we have the excitation energy of the band. We have the moment of inertia, or the rotational constant, big A, the slope of the band. And then for k equals a half bands, we also have the staggering parameter, little a, also known as the Coriolis decoupling parameter for the band. And we've seen that some properties are converged, some are not. So we saw, even in beryllium-9, we saw that the ground state band, so let's look at excitation energies relative to the ground state band. Sanity check. Excitation energies of the ground state band are all 0. Very well converged at 0, but that doesn't tell us anything. Excitation energy of the first excited band in beryllium-9 we saw was somewhat stable, but they were still, the two bands were still moving relative to each other. You could imagine that actually converging to a finite value here. There is, in the exercises, and we might discuss it informally if we have time. Actually, I do want to show you some slides on that informally. There is this question of extrapolating these results, seeing if from these results at finite truncation, can we actually figure out what the true results are? The answer is, we hope maybe we might be able to someday. There are some approaches that are being played with, but it's still very inconclusive. The unnatural parity band actually also seems to have pretty similar convergence going on here. But now if we look at those even mass nuclei, oh, also beryllium-11. Beryllium-11 is famous for its parity inversion. It's a little bit hard to compare. These are band energies rather than this energy of the band head state. There's different staggering going on, so it's very hard to compare this. In fact, in the experiment, the unnatural parity state is lower in energy than the natural parity state, so so-called parity inversion of the ground state. And that's actually the band parameters. It can be flipped slightly, but that's actually remarkably. These are 3 different points at 3 different n-maxes sitting right on top of each other. So that's surprisingly stable. I think there's a question there. Let me just finish this one comment. On the other hand, some of these other bands, these are the excited bands which plow through the valence termination. They are coming down very quickly. Who knows where they will end, and something, again, funny may happen with the band crossing. Was there a question here?
Is possible determining more excited states, and determining which quantum number they have?
Determine more excited states, meaning beyond the ones shown here. Yes. So the challenge is, so they're actually, that's a fun question. Let me backtrack then slightly to a very important point with the analysis here, which is as true in the theory here as it is typically in experiment. you have things going on relatively cleanly around the ERAST line. From this state to that state, for instance, is 40, 10, 15 MeV. You all know from perturbation theory that mixing matrix elements, their strength, if the strength of the mixing matrix element is bigger than the spacing between the states, then you're going to get heavy mixing of states. So you can very much imagine that even if you had the nucleus wanting to be rotational, somehow these things always get into anthropomorphizing, but then very slight perturbations would cause heavy mixing of states once you get up here. So even if there were some ideal picture in which you had good rotation, it would likely be messed up. For instance, we actually see cases where you have what looks like a rotational state fragmented over 2 states. That's when things are still relatively manageable. Now imagine what happens when you go there. All that said, you actually can get more information out than we're seeing right here using the SU3 approach of the LSU group. So actually a lot of things which are not entirely obvious looking at this can become much cleaner when you start looking at SU3 quantum numbers, which I will touch on a little bit after the break. But we've almost are at the end of this part of the talk, so let me just do the last slide. Okay, so we had excitation energies. We saw none of them are, the excitation energy of the bands are not terribly well converged for the most part. But we saw the bands, as we increased Nmax, increased our basis size, the bands moved down with pretty constant slopes. So those we can actually start to make real predictions about. The ERAS band slopes, they're still varying a bit, but they look, you can almost by eye guess where they might land. Yeah, that's always dangerous. Remember that warning on the first slide of this talk. Some components may be harmful. But you also start seeing some clusters, which we have already more or less seen. Remember, we saw the ERAS bands had steeper slopes. The excited bands tended to have shallower slopes. Here are those excited bands. Again, those slopes seem to be pretty converged at about half the excited slopes. Coriolis decoupling, this is just for the k equals a half bands, of course. That's pretty. You might even start to believe that the full space result would actually be somewhere in the ballpark of these. They're varying so slowly. Again, to be viewed with caution and hopefully with more rigorous extrapolation schemes in the future. Notice beryllium-7 has a negative staggering, which makes a very interesting thing. Its ground state, I'm so tempted to go back and show that. Anyway, the band head is not the lowest spin member. It actually goes spin a half, spin 3 halves, spin 5 halves, spin 7 halves. The coefficient is so negative. And that's exactly what's seen in an experiment. It's also what would be expected from the Nilsson model, which Rick will be covering. Not for that nucleus, but he will cover the Nilsson model. All right, now I'm going to go out completely on a limb. So take this with a grain of salt. Promise me you'll take this with a grain of salt. So if we compare, we can look in the literature and see, well, there are tentative bands assigned. And to avoid shenanigans, you know, if you're a theorist, you'll always pick the data that most matches your calculation, even if you think you're being objective. So I just blindly took, if there was a literature assignment for the band, I think there was for all but maybe one of these bands, I just blindly took the assignment without trying to judge whether it was based on anything or not, and plotted what the experimental values for and then took those experimental levels, fit them by the same procedures as fitting the data, and looked at the predictions. So beryllium-9, the excited band, and the unnatural parity ERAS band would be around here, which is very plausibly where those guys could be converging to, at least the right ballpark. Yeah, the question here isn't so much as if we've got it right, but are we horrendously wrong? The unnatural parity band, again, that's a couple of MeV precision we'd be aiming for. It's not horribly inconsistent. This excited band, it's rapidly converging, but it's not exclusive of the possibility that we could land where experiment is. Beryllium-12 looks pathological. Look, nothing we can do about it. And then, right, remember we're taking nucleon-nucleon scattering and trying to predict mass 12 out of it. So this could be an issue with the interaction itself, or there's still a lot going on with convergence that could change. These slopes, the slopes of the different bands, moments of inertia, that's actually pretty good ballpark. Most of them are even moving in the right direction with a couple of exceptions. Again, I would not have expected it to come out this, when I was setting out to make this plot, I did not expect it to come out this nicely. Obviously, again, there are exceptions, beryllium-12, beryllium-10, I'm not sure we'll ever catch up there. Beryllium-12, we're already off by a factor of 2. Interestingly enough, we mentioned that in experiment you have this negative scattering in beryllium-7 and, negative staggering in beryllium-7. It's positive staggering for most of the others. That's actually much better than I would have hoped for. But again, there's a lot to be determined here, and who knows where things will converge to. That's why I said big grain of salt. There's a lot of flexibility in some of the band assignments here, even if I wasn't the one who made the band assignments. But it's just it's fun to compare. It gives us some ideas. That is it for the first half of the lecture. I do have some slides which we can do after the break on trying to spell out the SU3 approach. And there will be some introductory slides there. I thought it would be nice to go back over some of the more general principles of group theory. Like there have been a lot of discussion of the Wigner-Eckhart theorem. I wanted to pull it all together, how that ties together with the generalized Wigner-Eckhart theorem. I have tied together some of the things you've seen in the past few days. So this is it for the first half.